atom that will install well, a series of interesting features that simplify the development. And after you install these, you will get an environment for Julia, which is the one we have here. So you will get this toolbar that is dedicated for Julia. So you have things like new Julia file and things to save files and so on. And I will now give you a brief overview of what it looks like to work with Julia. In the beginning, so I was using here, because I was developing a bit of Julia code a few minutes ago. In the beginning, you have just one large editor window where you can write whatever you want. So this is just a text editor, nothing fancy here, although it is tailored for Julia. And below you have the Julia read eval print loop. Okay, here I'm running a slightly older version of Julia. So this is 1.4, but release candidate 1, just because I was experimenting at the time. And since it's working well, I didn't update it yet. If you install Julia now, I think you will find version 1.4.1, something like that. So the job of a read eval print loop is to read, evaluate, and then print the results. And so here you can test very simple things like arithmetic expressions or calling functions or whatever. And one curiosity is that you can use Unicode if you want. And everything works as expected here. So this is like a glorified calculator where you can try things. But mostly you will be writing stuff on this thing here at the top. Because the read eval print loop is just for experimenting stuff. And in fact, I will show you that although you can use the read eval print loop, you can also do more or less the same thing in the editor. So, I mean, on this text file here, it is also possible to evaluate stuff. But we will start with very simple things, and then we will move on to more advanced stuff. So, very simple things about Julia. Well, Julia is a functional programming language. That means that it is based on functions. So you have to define functions for most of the stuff. Okay. And so I will start by defining a function. And the way you define functions in Julia is, well, actually you have two different syntaxes for defining functions in Julia. So the first one is the more mathematical. We are going to define function square, square of x, and you write something like this, x times x. So here we have a function definition. You might also have noticed that as I'm writing things, the editor is also trying to help me by giving me some feedback on the things I'm doing and what I'm supposed to use. So here it says, well, now what you write here is just text. It's just text, and you cannot use it. So if I try to here REPL to compute something, square of 2, I will get an error because it says square is not defined. Because what happens here in the editor is just text. And so you need to inform Julia that the text that you just wrote is actually a definition. And you want Julia to take that definition into account. There are several different ways for you to do that. The simplest one is to just go here, and you will see you have lots of options that you can click and do things. And fortunately, they also include some documentation. And you see here, one of them is the run block option. The other one is the run all option. So it depends on what you're trying to do. Here I will just run the block, and you will notice that it prints on the editor itself the result of the evaluation. And that's the case because for any expression that you write, if you do that thing, it works in the editor as if you were using the read eval print loop. Okay. Now, this number here, it's not something that you typed. So this is just a visualization of the result. It's not inside your text file. And so when you save these and then you load all of these annotations that you have here, you will not see them when you reload your file. So you need to always evaluate the stuff in order to see these annotations. So in fact, what we have here is just a kind of a visualization of the result of the evaluation. Now, given that I defined the function, my goal is now to use the function. And let's say I want to compute the square of 2. And again, you can either use this, or else you just follow the key binding, which it suggests us to use Shift-Enter thing. So if I try Shift-Enter, you'll see that indeed the function works. I mentioned that there are two syntaxes for defining functions. So let me give you another syntax for this. In this syntax here, they were trying to, well, I'm guessing they were trying to please the people from the Python community. And so in this syntax, you can write code that looks much more like Python. So I'm doing things here which are not entirely necessary, but it makes the function look more like a Python definition. And, well, you end up having the exact same thing, okay? So as you can see, you have two different syntaxes for the same thing. So I'm not a fundamentalist, so you can use whatever you prefer. I tend to use the mathematical syntax because I like it more, but you can use whatever you want, okay, or whatever you feel comfortable. Now, these two different syntaxes, they also exist for other forms. Okay, so for instance, a conditional expression in Julia can use again two different syntaxes. This is not a novelty because you have the exact same thing in the C language or in the Java language or in C++ language, although in those cases you have a justification for the two different syntaxes. Because a conditional expression in Java is something that is treated as an expression, while an if form in Java is a statement. In the case of Julia, there's no difference between them. So everything is an expression in Julia, but they still preserve the two different syntaxes. So let me define a function using now these two different syntaxes. So let's say factorial of a number. So the first syntax is to use the question mark. So if n equals 0, and you, by the way, you will notice that I'm using the two equal signs. So this is the, and in C, where comparisons use the double equal, while assignments, they are not really assignments, but they look like assignments, they use just the single equal. Another feature here of Julia is that Julia is insensitive to code indentation. So this is not like in Python, where you have those strict rules regarding things that you can place on one line, and then you have to use the colon in order to inform that, yeah, in Julia, everything is very flexible. So I tend to, when I'm writing a function definition, if it is bigger than one line of code, I tend to move to the next line. Okay, so that's what you see here. If it is really small, then I will write it on the same line. And so here I have that if n equals 0, we want to return 1. Otherwise, we want to return n times the factorial of n minus 1. Okay, so now I define the function fact, and if I use this, it should work as expected, and indeed it does. Now, using the other form, I will make it even more Python-like by changing the function syntax to become more similar to Python, and in this case, then I will return 1, else I will return n, times factorial of n minus 1. And now we need an end to complete the if form, and we need an end to complete the function form. Okay. Now, to be honest, the return statement is not needed. I include it here just to make it look more like Python, but it is not needed because differently from Python and differently from many other languages, Julia is expression-based, and expressions have value. And that means that the value of a function is just the last expression that is evaluated before the function ends. So when you look at a function and you see here, for instance, the if form, you know that there are two possible ways of exiting the function. Either the condition is true and then you exit from the true branch of the if form, or the condition is false and then you exit from the false branch of the function. And that means that the return is just for premature ending of a function. For instance, if you are inside a for loop or a while loop, and then you decide, yeah, okay, it's now time to return the value of the function, then you can, I would say, abruptly end the function executing by returning something. But in normal code, where you do not need to abruptly end anything, you do not need to use the return form. So although it looks more like Python, and it works, okay, so that there's no question about that. So if I just redefined the function, so if I try to use it, you'll see that it computes correct result. We can simplify it by avoiding the return form in this case. Sorry. And I'm redefining the function. As you can see, it doesn't change a thing. So far, so good. So simple function definitions. Any questions so far? Okay, so then let's move on. Let's talk a little bit about data types. So we have numbers, obviously, integers, but we also have floating point numbers. So 3.0, for instance. And you have the expected behavior that if you provide a floating point number to some operation, you will get a floating point number as a result, because these floating point numbers, they are contagious. So if you have operations involving floating point numbers, the result tends to be a floating point number. Now, these floating point numbers, they in fact are 64 bits. So 64 bits because I'm using Julia installation for 64 bits. Now, there is one operation called typeof that allows you to know a little bit more about these data types. So if I write the typeof operation, it will return the type of the value. And you can see here that the type of the number 1.0 is a float 64. If I try this with number 1, you'll see it is an int 64. Okay, so you have different types of integers. There are also int 32 and int 16 and int 8. And there are, as far as I remember, also floating point numbers with 32 bits. Okay. Now, besides integers and floats, you also have other data types. So Julia was designed for scientific computation, and so it also includes fractions, for instance. So as a starting point, uh, which type do you expect as a result of this expression? Can you guess? Or just write your guess in the chat. So what is the data type that you expect from the expression 1/2? Okay, exactly. So floating point. Because in this operation, 1 divided by 2 will be something like 0.5. And so in the end, you get a floating point number. But if you really want a fraction, I mean 1/2, then you can in Julia by using this double slash. Okay, so if I try this expression here, it will tell me that it is a rational, and then it also includes some additional information. It says it is a rational where the numerator and the denominator of the rational are int 64. Now, the reason why it prints the result like this is because Julia also includes parametric types, and the rational is a parametric type. And a parametric type is a type that has parameters. And so it might be instantiated with other types as arguments. And that's what is going on here. Okay, so rational is a parametric type, and it can be instantiated with the denominator. And hopefully everything will work as expected. So if I try this, oh, what is going on today? I'm writing everything. So say what is the square of this fraction, and it tells me the correct result. So one interesting feature about Julia so far, which makes it look like Python, is that we defined functions and we did not declare type. Function is generic by default in the sense that it takes several different kinds of arguments, and as long as the operations that the function uses are defined for those types, everything works as expected. Now, that's not the case of the factorial function. So the factorial function probably will only work correctly for integers, but that is the case for many other functions. However, it is also possible to provide types for the parameters. But the semantics then become slightly different from what you get in other programming languages, because Julia takes a lot of inspiration from Common Lisp in that regard. And whenever you define a function in Julia, what you're really doing is defining a method. Define generic functions using the def generic form, and then you can specialize those generic functions using the def method form. In Julia, in general, you do not define the generic function. Generic function is automatically defined for you, although you can if you want. And you only define methods. So every time I wrote one definition here, what I was doing was defining a method. Now, the surprising thing here is that, well, but I just said that the parameters were not typed, and I was not being entirely honest. In fact, every time you define a function in Julia, you are specializing a generic function, but on the most generic type that exists, which is any. Okay. So, in fact, all are more or less the same as writing them like this. And now this looks more like a method. So this is the syntax these two colons, this is the syntax in Julia to specify the type of the parameter. So what this thing means is that the square function is expecting values of more specific. So let's say that you want to define a square of a really specific type, let's say for, now I will do something really awkward, let's say float 64, and you will say that if you try to compute the square of a float 64 number, you will just return a string like this. So if I define terminology, I did not define any function, I just specialized a generic function, and in this case for float 64. So we already have one function here that is specialized for type any, and now we have another one that is specialized for float 64. So this means that the first one is still applicable to all arguments which are not float 64. So if I'm not mistaken, if I try this example here, it still computes the exact same result. However, if I try this example here, which is, I know 3.0 is a float 64, it now produces something different. Okay? So what you're seeing is this ability in Julia to specialize functions for different types of arguments, and the behavior that you get in the end is just the same that you have in the common Lisp object system. Okay, so what you define is a method, and the method specializes a generic function. Now, although Julia took a lot of inspiration from common Lisp, there are also very important differences. And the first one is that you do not get method combination. Okay, so in common Lisp, you have the standard method combination that allows you to define primary methods, and then before only have primary methods. Okay, you do not have these before, after, and around methods. And you do not have the simple method combination that you have in common Lisp. So common Lisp is more powerful in that regard because it allows you to use extra features of method combination, which do not exist in the case of Julia. But the other thing that does exist is multiple dispatch. So in Julia, you can define methods that involve multiple parameters with different types. So let's imagine I define function foo, and I will now specialize the parameters in different combinations of arguments. So for instance, let's say that foo, if it takes an x that is an int 64, and if it takes a y that is a float 64, then it will return int times float. Well, this time does not look good. Let me use this one here. Okay, sorry. And we'll now define another method that tells us that if I provide a float 64 and an int 64, then this is float times int. And now I will try to use them. So let's say 1 and 1.0. And it knows it's int type float. And if I try the other way, 1.0 and 1, you will get float times int. And the good news is that this thing is entirely dynamic. Now want to use I want to make function calls without even knowing the type of the arguments at compile time, it will work anyway. Okay. Now moving to additional types, the language was, as I said, designed primarily for scientific computation, and in scientific computation, one of the most used types is the array. which in Julia can be multidimensional. And then you have the simplest possible array, which is the vector, which is unidimensional. And although in Julia things tend to get slightly more complex because you have column vectors and row vectors, but you also have a kind of a default vector, which is what you get when you write expressions in square brackets. So 1, 2, 3, this is just here you can see the contents of the vectors and so on. So this is another data type, and obviously you can specialize functions in this data type, and you can even specialize them in, well, awkward combinations. Let's say we will extend foo to take an x that is a vector of int. Let me just close this thing here, here, int 64, and let's say that y is a vector of float 64. Okay, and in this case we'll say that we have a v int times a v float. Say, yeah, we have here a vector of ints. Let's try a vector of floats, and it works correctly. Okay, so it even deals with parametric types without any problems. Besides vectors, you also have tuples. So tuples use the same syntax as in Python. So anything that looks like a group of things, it answers indeed that's a tuple. And you can also specialize functions in tuples. Okay, although in the case of tuples, data types tend to become slightly more complex because then you have tuples with arbitrary size and things like that. You also have pairs. Pairs, they use this funny syntax, which is also described in the project, where if you write something like this is just a pair, okay? And it prints just like I wrote it, but in fact it's a pair. And we can, let's say, define my pair like this, and then I have pair 1, which is the first element. Well, probably I should have used something more interesting. Let's say foo points to 2, okay? And so pair 1 now it's foo, and pair 2 is, it should be number 2, okay? So plenty of data types that you can explore in Julia to do interesting things. You also have dictionaries. So dictionaries, they explore pairs, you know, to create a dictionary. So let's say A points to 1 and B points to. This is a dictionary, so if you inspect the dictionary, you will see that the entries that you provided now belong to the dictionary. So if I define my D dictionary as this, then you can use D A and you get correct entry. Okay. So lots of data types. But if you want, you can also define your own data types. Now, this is the area where Julia looks really bad, in my opinion. They have a justification for doing things like this. Again, it's always scientific computation. In scientific computation, you want to have performance, a lot of performance, and that means that the data type representation is extremely important. And if possible, they want to avoid pointers, because pointers is the thing that kills the performance in the modern CPU architectures. So if you have an array of numbers, for instance, floating point numbers, it is much more efficient to process an array of numbers than to process an array of pointers to numbers. Because every time you have to dereference a pointer, then it invalidates the caches in the CPU, and it gets much more problematic to do anything because the performance goes down. And so Julia was designed to have the more, I would say, more direct representation that is possible for data types. But the problem is that that does not make it very flexible for us when we want to have, let's say, structured information. So when you compare Java with Julia in what regard data types, you will see that Java is much more easy to create complex data structures than in Julia. It's not doable. Obviously you can do it in Julia, but it's not as flexible as in a language like Java, and much less in when you compare it with Common Lisp, for instance. So even in the case of Java, you have inheritance, you have interfaces, so you have lots of things that you can use in order to develop rich data types. Not in the case of Julia. Where we want to define something that looks like a record in C. In fact, it uses the same terminology. You use the word struct, and then you give it a name. Let's say whatever person, and then you provide a series of fields. Let's say we have a name, we have an age, and this is a syntax for such a record. Now, if I define this thing, then you can immediately start creating instances of that structure, because when you define a struct like I did, it will automatically define a constructor that has the same name as the structure you just defined, and the constructor takes as arguments the fields here. I did not provide any types. So I say, well, there is a name, there is an age, but given that I did not specify the types, they expect any as a value. And so that means that I can do whatever I want. So for instance, John, let's say 32. And this is one of those structures. Obviously, if you use the editor, you have this ability to introspect what is going on inside this object. So you see here the contents, but nothing prevents you from doing awkward things like, let's say, you just switch the order, and then you'll get something that is obviously wrong. Okay. So if you want to be more precise in the way you define things, then you need to include that the name is a string and the age is an int. Okay, so by default, int corresponds to int64. Now the problem is that if I'm trying to define this structure here, after I define the previous version of the structure, now Julie will complain. So if I try to define this, it says, well, you are trying to redefine something that I already assumed that had a different shape, and so it doesn't allow me to do that. So that's the moment where you really start to feel that this is different from Common Lisp. Because the only way out, well, there are other ways out of this. You will have to reuse modules and stuff like that. But in order to avoid making it more complex, this is the time where I just kill Julia and say, okay, let's start over again. Let's start again. And now if I try to define this, I will restart. Okay, create this guy here. Everything works as expected. The time you're seeing is taking is because it's now compiling that structure. Yep, correct. And if I try this, hopefully I will get an error and say, yeah, okay, you cannot do this. It complains that you are doing incorrect things. Okay, so any questions so far? Now, a problem that we have with these structures is that there is no inheritance between these structures. So if I want to define, let's say, a student as a subtype of a person, and this is the syntax for defining a subtype, then you will see that, and well, maybe you want to include some extra information like the school or something like that. And let me just be consistent. You will get an error. It will not allow you to define that because it is not possible to inherit from structs. Now, this is annoying because one of the advantages of inheritance is that you want to reuse stuff. But if you think about what happens in the C programming language, for instance, you also do not have inheritance between structs in C. What you can do is to include structs inside other structs. And that's also possible in Julia. So Julia here follows the C data model. So if you want to define something that, well, is a student, but also contains information that is related to being a person, well, then the correct solution is not to define these as inheritance, but instead as a kind of an inclusion, where you say, well, a student includes a person, and then it also describes the school. So you would do things like, well, define that the student contains a person, and then, sorry, I'm doing this in the opposite order. So let's say person of type person, and then we have a school, let's say, of type string. Okay, so if I try to do this, then it works correctly. Obviously now the syntax becomes kind of annoying because if I want to create my student, I will have to also create the person that is the student. So let's say that we have here Peter, and Peter is well, 16 years old, and he studies in some St. Mary's school or whatever. Okay, so I get my student, but it's not very natural to, at least nowadays where you used to inheritance and subtyping and things like that, it's not very natural to do things like this. But this is the Julia way of defining data types. Now, this does not mean that you have to define everything using this approach, okay? Because you can define an entire object-oriented system on top of this. Okay, so you can look at these struct things as the basis for, let's say, develop a more advanced object-oriented or whatever you prefer structuring approach. And that's what your colleagues last year did. So the project in the previous year was to implement something that would look like class definitions, the same ideas from Common Lisp, but now implemented in Julia, where you would also have multiple inheritance and, if possible, meta classes and so on and so forth. Okay, so that's, let's say, it's not an excuse for doing sophisticated stuff, but I would say that this is an area where Julia still needs to evolve a lot if it wants to be competitive. Makes this annoying is that now you will have to use a cascade of accesses in order to retrieve information. So let me go back just a little bit to the person object to show you that if you want to retrieve the fields, and let me remove this element here, which was wrong. If you want to retrieve the fields of an object, you use just the same syntax as you use in a language like C or in Java. Okay, so in this case, you will say, well, p1 dot name, and you get the name of the person. But if you go to the student, and if you want to know its name, then you know that now you have to use a cascade of things like, well, from S, you need to access person, and then from person, you need to access name. Okay. And that's kind of annoying. Now, there are lots of packages in Julia that simplifies these by defining some metaprogramming that allows you to automatically define a kind of a name operation in student that will go to the correct place. But if I was doing this just by hand, then probably this would be the time for me to define a getter. Let's say the name of a person. Let's say P is a person, and the name of P is obtained by, I have a function, and if I use the function, I get the name. And this is where then methods become very useful, because I can do the same thing here by saying, well, the name of a student can be obtained by using the exact same function, but now over student person. Okay. Which means that now I can just use name of S, and it gives me the correct answer. So in Julia, the idea is that you should rely on methods for most of your stuff. You should define methods for at all occasions, and then they will have the correct specialization depending on the data types that you are using. So if I'm applying these to a person, it will do one thing. If I'm applying this to a student, it will do another thing. And one of the approaches that you can use is to use metaprogramming to define these methods automatically. So it is possible for you to just say, well, I want to, given that student includes a person, I want to provide all methods that were defined for person also for student. And then it defines automatically this stuff here. But now, in order for me to explain that, I would have to explain how you define macros in Julia, and I do not want to do that now. Okay, so we might do that later, but not at this moment, because you are not required to use macros in the project. So that's just an extension. Questions so far? Now, although I said that there is no inheritance in structs, and that's true. There is, however, subtyping, but not between structs like I just did. So you have subtyping in Julia by defining abstract structs. Okay, and so the usefulness of the abstract structs is that it is possible for you to define methods on abstract structs, and then you can have a hierarchy of subtypes where the methods will be applicable to all the elements that are subtypes of a given type. So let me give an example. So you can define type abstract, sorry, she's on the correct. Let's say abstract type, and I will define a being. Okay, so this is just a type. It's like an interface in Java. But in these types, you can have subtyping. So I can now define abstract type human being, and then you can specify inheritance. You can say this thing inherits from a being. Yeah. Okay. And then maybe you would like to define a person, just like I did, as inheriting from these types. So I will move these just to make it more By the way, can you read what I'm doing properly? I can make the font bigger if you want. Um, so I can define being, I can define human being, and then I can say that the person is not a human being. Okay. Again, it complains because the struct was already defined, so you're not allowed to do this. So I will just kill Julia again, and I will try this once again. Say, okay, let's have beings, human beings, and now person. Okay. And this means that if you define, and I can also say that the student inherits from a human being. Okay. That's possible. So now I have a hierarchy of types, and I can create elements. Let's say John. Everything works as expected. I can define my methods as before. They work as expected. But I can also define methods. Okay. So let me just complete my example so to see that everything is working correctly. Indeed it is. And now I can define a method, whatever, say what is your name, and I can define this, say, on age, which is a human being. Okay. And I can be very flexible in the sense that I can use operations at any time, even if they were not defined precisely for human beings. That's not a problem, because the only thing you are specifying here is the applicability of the method. It says this method applies to anything that can be considered as a human being. And so here I will take the opportunity to show you string interpolation in Julia. So string interpolation allows you to do things like my name is, and now you can include here an expression that will be inserted in the middle of the string. So in order to do that, you will have to use this awkward syntax that they have in Julia, where everything that is between those parentheses preceded by a $sign will be evaluated, and the result will be included in the string. And here what I will do is to call the name function with the age argument. So if I define the function using, say, the person P1, it works correctly. If I try to do the same thing using my student S, it works correctly. Okay, so the only thing I was doing here is to define the applicability of the method, but then the method relies on this other method called name, which then is specialized on different types. So you can create a very flexible approach. So this is I would say, the functional part of Julia that is really well done, which is that you can use the exact same ideas that you learned in the common Lisp object system, where you can have methods defined on whatever level you want of your type hierarchy, and that only defines the applicability of the method. So the method now is generic in the sense that it applies to any type that is a subtype of human being. Okay, so it works correctly in all cases, even if it relies on methods that are not defined for human being. Okay, so that's what I'm doing here. So name was not defined for human being. It was only defined for student and for person, and not for human being. Another thing that might be interesting for you to know is that the process, the compilation process in Julia is, I would say, more complex than what you expect from any other language, because there are several steps involved. This is even more complex than in Common Lisp. And the reason is because when you define a method like I just did here, so this method here, The type that I provided here is, in a sense, just to define the applicability of the method. Because then the function was called with, in one case, a person, and in the other case, a student. Okay? And that means that the definition I provided here had to be compiled student. Okay, so there is a just-in-time compiler that whenever the method is applied to an argument, because it was described in terms of an abstract type and then it's being applied to concrete types, it will then be compiled for each of those concrete types. Okay, and then it is cached so that the next time the method is applied, it retrieves the result of the compilation. Now, this just-in-time compilation is needed for performance reasons. So Julia is always trying to generate the most efficient code at all times, but that means that you have a warm-up period in Julia. And that's one of the reasons why the first time you use a method, you will see that it always takes a certain amount of time. This is similar in a sense to what Common Lisp did with the method combination. So we talked about method combination, said, well, we need to combine the applicable methods. These need to be done at all times. So every time a generic function is called, you need to find the applicable methods and then you need to combine them. And that's a lot of work. And then I told you, yeah, okay, but it can be cached, and that's what it does. And here, although there is no method combination, there is a kind of a method specialization where it knows, well, even if a function was defined for some type, it might end up being called with different types as arguments. So that happened even with the square function here. Okay, so when we define the square function here, this is defined for any type. But then when we call the function with, say, an integer or a float, Julia wants to use, and that means that at runtime, the first time the function is called, you will see that it takes, and sometimes it's even visible, a measurable amount of time to first compile the function, in the sense that, well, I saw an integer, so I will generate code for integers, and so it always takes some time. You saw it, hopefully, there was a gear showing that it was compiling things, and then you get the result. Now, on the second attempt, it's very fast, but the first time is always, for each new type, it will always take a certain amount of time, and then on second try, it's faster. Okay. So, any questions so far? Obviously, this is a kind of a brief tour of Julia. And now, thinking a little bit about the project, I want to talk about the try-catch in Julia. And first I will define a function. Let's define our mystery function, mystery x. And this is a function that just throws something, okay, throw x. In Java, you can only throw throwables, but that's not the case in Julia. You can throw anything. Okay, so, and that's a good thing. Now, if I use this function, and I will use it here in the REPL, just to make it clear, let's say I call mystery1, you will get an error. Because when you throw something, Julia expects that someone will catch it. And if there's no catch available, you will get an error. It will be recognized as an error. So this is like when I said that when you're using a signal in the project, if the difference between the signal and the error is that the error always requires handling. So someone needs to handle the the thing. And here is similar in the sense that if you use throw, Julia is expecting that someone this. Well, we can handle this. Oh, and another thing, sorry, I was forgetting. The reason why I tried this at REPL is because REPL makes it clear that there was something wrong. Because if I try to do it here, so mystery 1, you will get something that says, yeah, okay, that's problematic, but it's not very clear. So you need to click here to see that there was something wrong going on, while here it says explicitly, this is an error, okay? Now, if you want to catch, you need to use the try catch form. So you try this function and then you catch the result. Let's call it R. And then you decide what to do with R. And in this case, I will simply return R. Okay, so this is the try catch form. And given that in Julia everything is an expression, what this expression here is doing is just throw out and then returning it. So if I try this, you will see that I got my 1. Now, this can get slightly more complex. So let's create here a cascade of function. Let's say something as simple as 1 plus mystery plus 2. Okay, so this is a slightly more complex expression. So if mystery was returning 1, I mean normally returning 1, the result would be 1 plus 1 plus 2, which is 4. Okay, but given that during the computation of that expression, mystery then throws a result, and that result is catched by the try catch, everything between the try and the catch is erased, removed. The computation is aborted. Okay, so that means that even in this case, you will get 1 as a result. Okay, so that's the logic of throwing something and then catching it. Okay, is that the entire computation that was between the place where you are throwing the result and the place where the result is catched, that entire thing disappears. Okay, so there's no mystery here. It works as expected. Now, one interesting thing here is that the thing that you throw does not need to be of any special type. It does not need to be an exception or a throwable or anything like that. And I would guess that this is useful for you to implement the block and the return from form, okay, that is requested in the project, because it gives you a certain amount of freedom regarding the kinds of things that you might want to throw and how you can throw it. Now, another feature that is important to understand is that even if you catch something, you do not need to end here. You can rethrow the thing. So if I'm using here the rethrow, well, I will just, to make it more obvious, let's say we'll print line something. Let's say I saw this, and then I will rethrow the exception. This means that you will see something being printed. I saw 1, but then you get the same error as before, because no one handled here, but then you said, well, you can proceed. So in order to really stop it, you will have to use another try catch. And now you will see that you get the message printed and then the correct result. So hopefully you will get some ideas from this example. Block and return from. Now there's another feature in Julia that I would like to talk about, which is higher order functions. So a higher order function in Julia is nothing special. It's just a regular function that takes a function as an argument. Okay? But if the function that is provided as an argument is the first argument to the function, let's call it f, and then you have possibly other arguments. So let's provide a specific example, and the simplest possible one is just to do this. Okay, so f is a function, so I will apply it, and that's all. So we can try to use this higher order, and let's say function sin, and then it works as expected. Okay, so higher order is a function that takes a function and it takes a number and then it applies the function to the number, and that's all. Nothing fancy. What is more interesting is that you can use this function in two possible ways. One is the one I just showed you, and there is another one that is very useful when the function that you want to provide as an argument is an anonymous function. So let's imagine, for instance, that instead of computing the sinus of p divided by 2, I want to compute the sinus times the cosinus of p divided by 2. Now, there is no such function predefined in Julia, so I will have to provide one. And the easiest way to do that is to just provide an anonymous function in Julia. Now, anonymous functions in Julia, they do not have the lambda. Just use something that looks like this. Sine of x times cosine of x. So this is an anonymous function. And it works as expected, nothing fancy. But it's kind of annoying to write these anonymous functions. And so Julia provides a slightly different syntax, which is also explained in the project description, where you would do things differently. You will, you will not provide the functional argument on the function call, but instead you will use the do syntax, which allows you to write things like this. It does the exact same thing. And to be honest, whenever you write something like this, the parser immediately converts into something that looks like this. Okay, because the function that exists, in fact, is expecting a function. The anonymous function will be generated from this do expression. Okay, and so this is just a special syntax that you have in Julia, but it allows you, in many cases, to write nicer looking codes. And that's what's being suggested in the project. So every time in the project I'm using a do syntax, you know that, well, I'm talking about a higher order function that takes a function as a first argument, and that function will be generated from the do part of the function call. Okay, well, it's arguable which one of them is more readable. I have to confess, it depends. I'm not fundamentalist, and so I know people that will say that the do syntax is much less readable than the other one. But I would say it all depends on the situation. If you are just trying to use, so for instance, in the first example, the one I wrote here, if you try to use the do syntax, it gets annoying. You can do it, but it gets annoying. So you have to do something like this, and then you have to invent a variable, which was not really needed. So let's say do x, sine of x, and it's clearer. Okay, I would say that the first one in this case is clearer than the second one. And then the other thing you can do is that you can specialize operators in Julia. So you can even define the concept of product of functions if you want. Okay, I'm not entirely sure if I will do this correctly, but it works more or less like this, if I'm not mistaken. So base asterisk. I'm not entirely sure if I'm doing this correctly. Okay, so I would have to look at documentation, but we can hopefully say things like this. If you want to multiply two functions, today, then I will return a function that applies f of x and multiplies the result of applying e of x. I think it requires something like this. Well, I will have to look at documentation. If anyone remembers the syntax for defining Julia operators, just give me a second and I'll try to find in documentation Julia defining, because this thing it changed. Oh yeah, okay. So let me try that one. Exactly. So I would even argue in this case that it would look nicer if I just wrote sin times cosine applied to p, sorry, divided by 2. And as you see, it looks much nicer. Okay, so in the limit, you can even multiply functions between themselves, and then you can hide some of the complexity of the things you're doing. So it all depends. So from time to time, I will use this. Some other times I will not, and I will just take advantage of the abilities of Julia to do more functional programming. For instance, the composition of functions, it's a very common case. So let's say you would like to do something that looks like this. So I'm getting tired of defining this function, but let's say you want to compute the sine of the cosine. Sorry, I forgot the variable. So let's say do x sine of cosine of x. So if you try to do this, then it becomes much easier because this is even predefined in Julia to just write sine and then circ cosine and then p divided by 2. Much nicer. Okay. So it all depends. So questions. Anything you want to discuss regarding the project? Or maybe it's easy if you ask questions. Well, in which are you asking about the language in which? Oh, it's used. Well, nowadays there is. They say that it's a very well-paid job because there are lots of finance that is using Julia. Because finance nowadays is mostly a data science activity. So they are always trying to find trends in where they should invest money and so on. So I can try to give you a few links if you want. So Julia at this moment is used a lot for data science. And so I can give you a few pointers if you want. Where is my chat? It just disappears. I'm not sure about that. Regarding the exam, I will have to confirm with the coordinator. I know that we have at the end of the week to define all of that stuff. So far, I'm just following the same dates that were that department decided. Uh, I will have to check, but I will make an announcement anyway. So I know that we have until Friday to define the way the exam will be done and on which dates. But everything must be coordinated with the other courses, as you might guess. So we cannot have collisions. And so I cannot give you any precise answers at this moment because I need to wait for the decision from the coordinator of the master. And so he's the one that is taking all the dates into account and trying to avoid collisions. So I think this was my tour. Yeah, we will have to have an online exam. So everything will be online until the end of the semester nowadays. And that's for all courses. It's not only for this one here. Um, yeah, so this is I would say interesting. So interesting is a funny word, but the situation we are living is interesting in that regards because everything is new. So we'll have um, yeah. Well, if you have any ideas, um, is it a try? Um, well, the problem is that we cannot do exams with people in the rooms at this moment. So it's forbidden. So that's the problem. I would prefer, obviously, to have the traditional exams, um, but anyway, these are not normal times, so we have to improvise. So, any questions? Anything you want to discuss? We still have time. So, if you want to talk about the project or something like that, yeah, that's a fact. And well, then you can guess if you have kids at home. Yeah, that's a problem. So I have my kids, and 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 it makes things more complex, obviously. And then it's interesting. I'm surprised that my internet is still working because they are having classes at the same time. So there are four online classes at the same time in my house. That the internet is working. Yeah, well, we need to compliment the internet provider. Okay, now apart from this, so as I said before, one of the reasons why I want you to do the project in Julia is just because I want you to be exposed to some well, I would say non-mainstream programming language. So everybody is very used to Java, and that's the thing I want to avoid. Because when I had your age, I was learning languages that really they were changing a lot. So there were new languages being proposed almost every month, and it looked like the sky was the limit. And nowadays you have these really huge programming languages like Java and C Sharp and so on. And whenever there is a new programming language that is being proposed, it's very hard for it to survive. But the important thing here is not for you to learn something that will give you a programming language for your life. That's not reasonable. Hopefully, you will survive all the programming languages that you learned. And the goal is for you to take ideas from these programming languages and then to apply them, even if you are forced to use something like Java. Okay? Because languages still evolve. And well, I know that I had to wait 20 years to have lambdas in Java, but it was obvious for me from the beginning that they would have lambdas. So I was already developing Java code where there was something very similar to a lambda, except that I had to use a really awkward syntax because I had to write anonymous inner classes. And then I decided to just keep using Java, but using a different syntax. So I developed my own uh, preprocessor that would generate Java way I preferred to do. So if there was a problem where anonymous functions would be a good option, that's the thing I would like to have in whatever language I'm using at that moment. Okay, and so that's one of the reasons why I think it's good for you to be exposed to other paradigms and other programming languages, because then you will get interesting ideas that you might want to apply even if you are using C or Java or whatever language you are forced to use at that time. Take these as a kind of a punishment that I'm applying just because I'm a fan of Julia, because I'm not. So I'm using Julia, but I have, well, there were much better languages in the past that did not survive. And so anyway, Julia has lots of interesting concepts, and that's one of the reasons why I want you to start reading a bit about Julia. Maybe next. Okay, so questions. So if there is nothing, probably we can end today. So it's my opportunity to compensate for all the minutes, extra minutes that I took from you. Um, and so, as usual, stay safe, work on your project. And if you have any questions, either send me emails or else or maybe you can schedule office hours. So I know that there are certain people which already requested office hours, and I'm scheduling office hours with them. But feel free to ask me anything or to request office hours. Okay. So I'll see you. Bye bye then.